Okay, so let's start this third lectures. So we finished last week by deriving some monotonicity properties of these random cluster models. This week we are going to see how we can use that first to define infinite volume measures, second to explain how the magnetization property, so having positive magnetization, is related to the long-range order property. And depending on time, we will start and maybe go quite far in the derivation of the exponential property in the subcritical regime. So how we relate the exponential property to the magnetization property, for instance. But before that, as I said, we start with infinite volume measures. So definition of infinite volume measures. So this is, I don't remember exactly which number, but let's say it's n. So up to now, we defined the random cluster measure on a finite graph. So G was finite. My goal in this section is to explain to you how one can derive a measure on Z2 and to derive a few properties of this measure. So definition. We are going to take the simplest definition that one can think of. So let phi Z2 PQ be the weak limit of the measures phi lambda n PQ, where lambda n is the box of size n around D. So this is the definition. Similarly, so at this point it's not clear at all that the limit exists, but we are going to justify that this weak limit is defined. But similarly, before doing that, let me define the second infinite volume measure. Let phi 1 z, this is not Z2, it's ZD, sorry. ZD PQ be the weak limit of the measures. And here I'm going to take phi lambda G PQ. Okay, so if I take the measures on lambda n only, then I end up with the first measure that I call phi 0 ZD PQ. And if I take the measure with the additional ghost that we explained last week, that we introduced last week, then you end up with another infinite volume measure. And this measure, a priori, is not the same as this one. We will discuss this during this class in several places. So in order to make a distinction between them, I call the one phi 0 and the other phi 1. Okay, just a reminder. Here, what do I call weak limit? I said that mu n converges weakly to mu if for any function x which goes from, from 0, 1 to a certain graph G into C, where G is finite. Then mu n of x converges to mu of x. Okay, so what does it mean here? It means you take an observable that depends on the edges in the graph G, G is finite. Then as soon as n is sufficiently large, G is included in the box of size n entirely. So you can make sense of phi lambda n pq of the random variable x. And you look whether this converges or not to this thing. So you say you have weak convergence, meaning that this apply at x when n is sufficiently large that it makes sense to speak of the average of x. This thing converges to this. Okay? To the average for this. Okay. So this is the definition. Now you will agree with me that it's not clear that there exists a measure that will be the limit that will satisfy this property. So why is this limit well defined? A priori, it could be that there exists a function x for which phi lambda n pq of x doesn't converge at all. And then a priori, you cannot make sense of this thing. Okay. So in order to prove the existence of this measure, we are going to use the monotonicity properties that we derived last week. More precisely, observe, so this is just a nice exercise that I leave to you. Observe that every random variable x, depending on finitely many edges, so any observable of this kind actually can be written as a linear combination of random variable of the form indicator of an increasing event, of indicator of A for A increasing event. So if I can prove the convergence for any indicator of an increasing event, then I will have convergence for any random variable depending on finitely many edges. So this is, again, this is just a very general fact. It doesn't depend on the measure at all. It's just when you look at a random variable depending on finitely many edges, you can write it by inclusion, exclusion, first for the events, and then by simply writing x as the sum of the possible values of the value times the indicator function that the x is equal to this value. So by doing these two steps, you can see that you can always write it as a linear combination of indicator function of increasing events. So here I should say it's not so clear, so let me write it like that it's clear that I mean increasing events. Okay, so why is this good? Because if I look at phi lambda n pq of an event A, well, remember that I explained last week, this was maybe the last comment of the class last week, I explained that when n increases, then the measure increases as well. So if I took an increasing event A, phi lambda n pq is smaller or equal to phi lambda n plus 1 pq of A. So if A is increasing, because this graph includes this graph as a subgraph, then I have this inequality for every n. But if I have this inequality for every n, this is simply an increasing sequence which is clearly bounded by 1. Therefore, it converges. To a value which for now I'm going to call phi of A. It's just a number between 0 and 1. So for every increasing event A, I end up with a good candidate for the value of the probability of the event A under this measure. At this stage, it's not entirely clear that these phi of A are consistent in the sense that they really give rise to the probabilities of a given measure. For that, you need to satisfy, you need to check that they are, that the phi defined like that, which is a perfectly fine function on increasing events, will give rise to a measure, is a measure. So first thing you need to prove is you need to define phi on any event, and you do that by linear combinations. And then you need to check that phi is indeed a measure. But the good thing about it is that if you restrict your attention to events that, say, depend on the box of size 1 billion, then the phi lambda n pq of the events in this box, they exactly satisfy, they are coherent because they come from a measure. So the coherence of these things give rise to a coherence for the limiting object. So by this simple observation, it is easy to derive, to check that phi gives rise to a measure, which we call phi ZD PQ. Okay, so that's to define phi 0. If you want to define phi 1, it is also possible. What is going to happen is that when you are going to do your reasoning, if I put here a ghost, what changes is that the measure with a ghost, when you imagine this additional vertex being connected to everybody, in some sense, you can imagine that this is the box lambda n plus 1 with a ghost. Okay, so the box one layer bigger with an additional ghost, where all the edges here, all these edges like that goes around, have an intensity equal to 1 that gives rise to a single ghost, to a single vertex. So in some sense, lambda n ghost can be seen as lambda n plus 1 ghost, where some edges are of intensity 1. So that are of p equal to 1. So by monotonicity, having lambda n plus 1 g with intensity p on the bound on these edges is smaller, is a measure which is smaller than having the same measure with intensity 1 on the boundary. So here, in this case, it's going to reverse the inequality. And now this quantity, this sequence is a decreasing sequence, so you can also make sense of the limiting value, and then the coherence of the limiting value follows from the same reasoning as for the first one. Okay, so that justifies the fact that the weak limits exist. Okay, let me check with you now what are the quantities that we were discussing. So in particular, if you remember properly, we were considering the magnetization So this is a remark, but a very important one. The magnetization was the limit when n tends to infinity of phi lambda n ghost PQ of 0 connected to the ghost. But now that we have a notion of limit here, this quantity actually converge, or can be written as phi ZD PQ1. So this is taking the limit of these events. And the 0 related to the ghost, then you can easily see that this event is going to converge to 0 connected to plus infinity, meaning here I'm doing some kinds of meaning that 0 is in an infinite connected, in infinite cluster. Okay? So here, notice that I'm doing a double limit, right? I'm taking the limit as n tends to infinity of a measure and also of an event. In some sense, this is, a random variable or an event an, so I'm taking mu n of an. But an is clearly bounded from both sides, so it's fairly easy to check that you end up with this quantity, and I'm not going to do it. Okay, so the phase transition at beta C magnetization in the random cluster model, it corresponds to the transition between the non-existence of infinite connected, of clusters, of infinite clusters, and the existence of an infinite cluster touching 0. Now, one thing that I would like to discuss now is that here we see that the existence of an infinite cluster touching 0 becomes an important property. So one thing which is natural is 0 playing a specific role in my construction? Or could I put any vertex here? So property phi 0 ZD PQ and phi 1 ZD PQ are invariant under translation. Meaning the following, meaning that for any event A, phi ZD PQ 0 or 1, depending on what you want to look at, of A, is equal to phi 0 or 1 ZD PQ of tau xa, where tau x is the translation by x in ZD. So if I take a vector and I translate the measure, I end up with the same measure. And the second property I want to prove is that these measures are ergodic. And ergodic means that for any A such that tau xa equal A for every x, we have phi 0 or 1 ZD PQ of A, which is either 0 or 1. Okay, ergodic in the standard sense of measure theory. So you see this, for instance, has a natural consequence, which is that when there exists an infinite cluster, it exists almost surely. So as a consequence, before I prove this property, phi 1 ZdPq of there exists an infinite cluster is belonging to 0, 1. Why? Because the existence of an infinite cluster is clearly an event which is invariant under translations. So when I put all of that together, what do I get? I get that there exists, so one can define PC, which is a number that depends on D and Q, belonging to 0, 1 a priori, such that PC is the infimum of the P such that phi 1 PQ, ZD PQ of 0 connected to infinity is 0. And this, by invariance under translation, if it's 0 for 0 connected to infinity, it's 0 for x connected to infinity for every x. Therefore, it means there is no infinite cluster, because if there is an infinite cluster, then there exists a point among a countable number of points which is connected to infinity. So this is also the infimum, sorry, it's the supremum. It's also the supremum of the P such that phi 1 ZD PQ of there exists an infinite cluster is 0. This is by invariance under translation. And by monotonicity, it's also the infimum of the P such that this quantity is strictly positive. This is monotonicity that gives you that. Of course, the monotonicity of the finite volume measures gives you monotonicity of the infinite volume measures. This I let you check it. It's a very simple property. And this is also the infimum of the P such that this quantity is equal to 1, because as soon as it's strictly positive, it must be equal to 1, since it belongs to 0, 1. Okay? So there is a critical point that is distinguishing between the subcritical, I mean, between a regime where there is no infinite cluster and a regime where there is almost surely an infinite cluster. Notice also that by this observation, I can relate this number to the critical parameter with magnetization of the Q-state Potts model. So when Q is an integer, I can also write this as minus Q minus 1 over Q log of so I can write this as exponential. So when Q1 beta C of Q is equal to minus Q minus 1 over Q log of 1 minus PC of D and Q. So I can relate the critical point of the random cluster model with the critical points of the Potts model. Okay. So how do I prove this proposition? So let's start with property 1. And you will agree with me that in order to be able to prove this property for any event A, by measurability, since every event A is well approximated by, is approximatable by, that's not a word, but can be approximated by events depending on finitely many edges. It's sufficient to derive this property for events that depend on finitely many edges. And second property is we saw, I told you earlier that any event which depends on finitely many edges can be written as by inclusion-exclusion in terms of events that are increasing and depends on finitely many edges, or events that are decreasing by complement and depends on finitely many edges. So it's sufficient to derive, for instance, for phi 0, to derive this property for events depending on finitely many edges that are decreasing, and for phi 1 that are increasing. So let's take phi 1. So let A be an event depending on finitely many edges that is increasing. Then phi 1 ZD PQ of A is the limit when n tends to infinity of phi 1, or let's maybe not write it like that, but let's say that phi 1 lambda, phi ghost lambda n PQ of tau x of A. If A is an event depending, so let's say A depends on the edges in lambda n, capital N, and let's say that X is of size K, is of norm K, infinite norm K, then this, well, this by definition is going to be larger or equal, smaller or equal than phi tau x lambda n minus k ghost PQ. So what did I do? I just observed that this graph here, so I have lambda n, and I'm just translating. Here I'm looking at the translate, let's say x is here, this is 0. I'm looking at the translate of n minus kg by x, and observing that this graph is bigger than this one, which means that this one, remember, the ghost is kind of saying that every edge outside the box is of intensity 1. So this guy can be seen as this graph with many edges with intensity 1. So that means that this measure is bigger than this measure. If you would do it without the ghost, you will have that this graph is included in this one, and therefore you will get the inequality in the other direction. Okay? But I chose to go with the ghost one, so I get this. Now letting, and this of course is just phi lambda n minus k ghost PQ of tau xa. So letting n go to infinity by taking n minus k larger than capital N to be able to make sense of these events, and then letting n tend to infinity, one gets that phi ZD1 PQ of A, which is the limit of this quantity, well, is smaller or equal to the limit of this one, but having n tend to infinity or n tend to infinity or n minus k tend to infinity is the same, so I end up again with this limit. So that gives me one of the inequalities. Okay? But notice that what I did also works. So similarly, I also have that phi tau x lambda n ghost PQ of A. Well, it's also larger or equal to phi lambda n plus k ghost PQ of A. Exactly for the same reason, which is that this graph is included in this one, and the ghosts correspond to saying that all the edges that are in this but not this have intensity 1. So I get the inequality in the other direction. But then letting n goes to infinity gives me the other inequality. Maybe I can write it. So it gives lambda 1 ZD PQ of A larger or equal to phi 1 ZD PQ. And here, of course, this is stupid. Sorry, I forgot the tau x here. And here's the tau x. What did I do? I mean, the other inequality. Okay, I think I just screwed everything. What did I do? Sorry about that. It's not that easy to be in front of an empty room. I mean this, sorry. Yes. So now when I do here, I get tau x of A on the right, and overall, we deduce that phi 1 ZDPQ of A is equal to phi 1 ZDPQ of tau xa. Since this is true for any increasing event depending on finitely many edges, by inclusion-exclusion it's true for any event depending on finitely many edges. And by extension, since any event is approximatable by, can be approximated by edges depending on event depending on finitely many edges, you deduce invariance under translation. So the result. So the invariance for other edges can be deduced first by inclusion, exclusion, and then by approximation by events depending on finitely many edges. Okay, so this is for property 1 for the invariance under translation. Let's now take a look at ergodicity. So for ergodicity, we are going to use a property. So again, because you can approximate event by event depending on finitely many edges, in this case, there is a natural relation between ergodicity and another property. So ergodicity is equivalent to what we call mixing, which means that for any event A and B, depending on finitely many edges, phi ZD1 PQ of A intersected with tau x of B, this converges as x tends to infinity to phi 1 ZD PQ of A times phi 1 ZD PQ of B. So if I can prove mixing, I would have proved ergodicity. Again, by inclusion-exclusion, I can focus my attention on increasing events. So if I focus my attention on increasing events, notice that first thing, I'm going to prove this by two inequalities. So first thing, if A and B are increasing, then phi 1 ZD PQ of A intersected with tau x of B is larger or equal by FKG, is larger or equal to phi 1 ZD PQ of A phi 1 ZD PQ of tau xb. Indeed, A and tau xb are increasing events. And then this, by invariance under translation, this is just phi 1 ZD PQ of B. So very good. At least the lim-inf of phi 1 ZD PQ of A intersected with tau x of B is larger or equal to the product of the probabilities. So we only need to prove the other inequality. And for the other inequality, notice that this is smaller or equal by FKG, that phi 1 ZD PQ of A intersected with tau x of B, knowing the events En, where En is the event that all the edges. So what I'm going to do is I have 0, I have a box of size n, an event A that depends, for instance, on the edges in that. I have x, I have the box of size n, lambda n of x around, tau x of lambda n, which is the box of size n around x. I have B here, and En is the fact that all the edges that are not in these two boxes are open. So all the edges with both endpoints outside lambda n union lambda n of x are open. So this is a nice increasing event. Since this is increasing by fkg, you have this. But now, imagine that A and B depends, so are increasing and depend on edges in lambda capital N. So for n larger or equal to 2n, maybe strictly larger than 2n, actually, two n plus 1, so I mean larger or equal to 2n plus 2, to be safe. If n is larger than that, and that all these edges are open, what does it tell me on the measure condition on that? Well, check very easily, but that tells you that in this box you see exactly the measure with lambda n with a ghost, and here the translate by x of the measure with lambda n with a ghost. So this is automatically equal, in this case, it's equal to phi 1 lambda n ghost pq of A times phi 1 lambda n ghost pq of B, where here I just use that, in fact, it's tau x of B, but it's also on the translate of the measure by x. So when I translate back everything to the origin, I end up with that. And there is no 1 at the top here. Yes. But by letting n go to, x go to infinity, by letting x go to infinity, so notice that here, in order to say that, I needed x to be large, so maybe x had to be also larger than x had to be larger than something, so n, maybe larger than 1/2 of x or something like that. So if x is sufficiently large, so when x tends to infinity, I end up with the fact that the lim sup, this time, of phi 1 zd pq of A intersected with tau x of B is smaller or equal to phi lambda n ghost pq of A phi lambda n ghost pq of B. And this is true for every n, which is larger than 2 capital N plus 2. So by letting n tend to infinity, we obtain that the lim sup is smaller than phi 1 zd pq of A phi 1 zd pq of B. And this is the end of the proof, because we proved that the lim inf was larger or equal to this quantity, and the lim sup is also smaller or equal to this quantity. So lim inf and lim sup are equal, and the limit exists and is equal to what we want. So this was for the ergodicity. We are going to make a break, and when we come back, we are going to try to relate. Now we have a relation between beta C and beta C mag, so the magnetization. In the second half of these lectures, we are going to try to relate beta C magnetization and beta C long-range ordering. So first by translating to the random cluster model, and then trying to prove something on the random cluster model. Thank you. Okay, so we introduced infinite volume measures. We proved that they were ergodic and invariant of the translations. So now I want to use these different facts to relate the property of long-range ordering and the property of spontaneous magnetization. So this is n+1 long-range ordering vs magnetization. So recall, so what did we say? We said that magnetization, this is equivalent by the Edwards-Sokal coupling, by the coupling between the Potts model and the random cluster model. This is the probability that 0 is connected to infinity is strictly positive. Okay? So it tells us that beta C magnetization is related to the critical points that we introduce of the random cluster model. Okay. Now, the long-range ordering, remember, is something about the infimum over x of sigma 0, sigma x, ZD beta, being strictly positive. By the long-range ordering, by the coupling with random cluster model, this infimum here, this quantity is related to the random cluster model on ZD. Since here I'm taking the measure, the standard measure, I'm looking at 0 boundary condition, and I'm looking at 0 connected to x. So at this point, it's interesting to try to compare this property with this one. So what differs? First observation is that here we are looking at the one boundary condition, while here we are looking at the 0 boundary conditions. This is the first distinction, and notice that these two measures have a priori no reason to be equal, so they may have very different behavior. The second thing is that here we are looking at 0 connected to infinity, while here we are looking at 0 connected to x. But we are looking at the infimum over x, so x could be farther and farther away from infinity, from 0, sorry. So, for instance, it's kind of easy to see that for this infimum to be positive, it's important that the probability for the 0 thing, so for infimum over x in ZD of phi 0 ZD PQ of 0 connected to x, for this to be positive, we must have that phi 0 ZD PQ of 0 connected to infinity is strictly positive. Why? Because if it's finite, if this is 0, by measurability, for every epsilon, there exists a capital N such that 0 connected to distance capital N is smaller than epsilon. But then, a fortiori, this probability is smaller than epsilon for every x, which is farther than distance capital N. But since this is true for every epsilon, it will imply that this infimum is 0. So this must hold. And notice that we proved in finite volume that phi 1, I mean phi lambda n ghost PQ is larger than phi lambda n PQ, with stochastically dominating. So here, by taking n to infinity, we immediately get that this is also true. So this is since phi 1 ZDPQ stochastically dominates phi 0 ZDPQ. So that here tells us that the long-range ordering implies the positive magnetization. Long-range ordering beta implies mag beta. So this inequality is trivial. I mean, trivial. It's not difficult. Now, how do we go in the other direction? Well, in the other direction, it's natural to try to relate this to the fact that 0 or x is connected to infinity. So you can look at phi 0 ZD PQ of 0 connected to x and say that a way of getting that is to have 0 and x in the same infinite connected component. Okay? So phi 0 ZD PQ of 0 and x belong to the same cluster, infinite cluster. So now here, two things can go wrong to compare this to the probability that 0 is connected to infinity for phi 1. First thing that can go wrong is that phi 0, as I said earlier, could be completely different from phi 1. But there is a second thing that could go wrong, is that imagine that even phi 0 is equal to phi 1. Okay? We have no problem here. We put a 1. Then we know that 0 is connected to infinity with positive probability. We know that there exists an infinite cluster with probability 1. This is very good. So we can assume, for instance, that 0 and x are connected to infinity because these are increasing events. So by the FKG inequality, this probability would be larger than the product. I mean, that the probability that 0 is connected to infinity times the probability that x is connected to infinity. So this will be positive since I want to prove that magnetization implies long-range order. But these two vertices, they have no reason to be in the same infinite cluster. Indeed, there could be that there are infinitely many infinite clusters, for instance, or finitely many, but not one. And in this case, well, it could be that 0 and x are connected to infinity with positive probability, but that the fact that they belong to the same cluster has a probability that tends to 0 when x tends to infinity. So here, we are going to prove, and this is going to be here, so theorem, phi 0, and in fact, you could also put 1 ZDPQ of there exists infinitely many, I mean, there exists more than 2 infinite clusters. We are going to prove that this is 0, always. If you have this property, here, this event is equal by the theorem below is equal to 0 and x belong to an infinite cluster. They don't need to be in the same, or let's say I'm going to write it like that. 0 connected to infinity and x connected to infinity. I don't need to impose that they belong to the same infinite cluster. Why? Because they cannot be more than 2 anyway. Okay, but now by FKG, this is phi ZD PQ 0 of 0 connected to infinity times the same probability for x, but by invariance under translation, I can put a square here. So this is starting to look much better. It's much closer to this one, but still we have a problem that it's not equal to the one we want. So a second property we are going to derive. It's not equal because it's not the same measure yet. It's phi 0, while the other one is phi 1. So we are going to prove a second theorem, which is going to tell me the following, which is that phi 0 ZD PQ and phi 1 ZD PQ coincide except on a countable family of p's. So for every fixed q, in fact, there is only finitely many p, countably many p, for which phi 0 is not equal to phi 1. So with these two theorems, with these theorems, we get that for all but countably many points, many p's, magnetization, infimum over x of phi 0 ZD PQ of 0 connected to x, strictly positive, implies phi 1, is implied by phi 1 ZD PQ of 0 connected to x, to infinity, is strictly positive. Why? Because for all but countably many points, this is equal to this, which is bounding this thanks to this theorem. Okay, so we go from there to there using this theorem, and then we go from there to there using this theorem. But because this is true for all but countably many points, what it immediately implies is that, so corollary, beta C long-range ordering is equal to beta C magnetization. So it is not true that the long-range ordering property is equivalent to the positive magnetization. In fact, it's even wrong for large Q in dimension 2 or in any dimension. It's wrong at beta C. So at beta C or at PC, we will see maybe in these lectures, but otherwise I will refer to it later on with the right references, that it is possible that at PC this is true, but this decays exponentially fast. So it's even the farthest away from the property that we can imagine. But it is true only at countably many points. So in particular, it is still true that the beta C, the corresponding parameters are equal. So the only point where it can fail is at the critical point. Okay. So I'm a little bit torn apart. I like the proof of this theorem, but it happens that for the SwissMAP lectures, people actually already saw this theorem for Bernoulli percolation in the class of Vincent Tassion. So this is called the Burton-Keene argument, and it was done for was done for Bernoulli in the lecture, so for Bernoulli percolation in the lectures of Vincent. And one thing which is easy to check is that in these lectures, Vincent only used the fact that whatever the conditioning on every other edge, an edge is open with probability which is bounded away from 0 and 1, and ergodicity and invariance under translation, which I just proved. So I'm not going to redo the proof of this theorem, and I refer to the lecture notes of Vincent for this theorem. Let me prove this theorem, and that will be the end of these lectures. Okay, so there are several ways of proving this theorem, but there is one that I particularly like, which is using, so, I mean, why is it going to be true that it's true? I mean, how are we going to prove that it's true except at countably many points? We are actually going to prove that it's true except at the non-continuity continuity points of an increasing function. And the thing is that it's well known that the points at which an increasing function valued in R and starting from R is non-continuous, so sorry, I restart. The points at which an increasing function from R to R is non-continuous are countable. This is a classical exercise that you can do in elementary school. And this is what we are going to use here. In order to do that, we are going to proceed in two steps. First, I'm going to prove some kind of criterion, and then I'm going to apply it to prove what I wanted. So first criterion is observe. So claim 1. If phi 0 ZDPQ of an edge is equal to phi 1 ZDPQ of an edge, then phi 0 ZDPQ is equal to phi 1 ZDPQ. So if the edge density of the two measures are equal, then the measures themselves are equal. Okay? In fact, it's an if and only if, so I can even write it like that. Why? Because if the two measures are equal, then automatically I have that. So this is an obvious. And for this thing, well, for this thing, let's consider Pn be the coupling between, I mean, the increasing coupling between phi lambda n pq and phi lambda n ghost pq. Okay, so I consider the increasing coupling between these two, which is given by the fact that this graph is larger or equal to this graph. So I have this increasing coupling. Remember that this, when n tends to infinity, converges to this, and this converges to this. Let A be increasing and depending on finitely many edges. Let's say they are in lambda capital N, where capital N is fixed. And let's just look at the difference between the probability of A in the first and in the second measure. So if I look at phi lambda n ghost PQ of A, and I subtract phi lambda n PQ of A, if I look at this, this inequality is simply due to the fact that lambda n goes stochastically, I mean, this measure stochastically dominates this one, and A is increasing. But here, I can also say this is Pn of omega, let's call it ghost, belongs to A. Or, I mean, I think it was prime, and omega doesn't belong to A. So the big configuration belongs to A, but not the small one. For this to occur, it's clear that one edge in the box of size capital N must be open in omega prime and closed in omega. We know that anyway, every edge which is open in omega prime is open in omega. So the only way that I can have a difference is that there is an edge which is open in the big configuration, but not in the small one. So it's smaller than the sum of the edges in lambda n of Pn of omega prime E is equal to 1 and omega prime and omega E is equal to 0. But this here has a simple formula. It is phi lambda n ghost PQ of omega E minus phi lambda n PQ of omega E. Note that this sum is finite. So now if n tends to infinity, what do I get? I get that 0 is smaller or equal to phi 1 ZdPQ of omega E minus phi 0 ZdPQ of omega E. Sorry, not of omega E, of A. This is the limit here. And now if I use this bound and I use the limit here, it's smaller than sum of the E in the edges of lambda capital N. And here I get phi 1 ZdPQ of omega E minus phi 0 ZdPQ of omega E. But my assumption in this direction is that this is true for an edge, but by invariance under translation for every edge it's true. So if this is equal to this, that means that this is equal to this. That means, because I have a finite sum here, that this is equal to 0. So I get that for any increasing event depending on finitely many edges, phi 1 of A is equal to phi 0 of A. And by inclusion, exclusion, and then by approximation, I get that for every element. So that gives me phi 1 ZdPQ is equal to phi 0 ZdPQ. So this is the proof of the claim. Now, how do we use that? So the argument is going to be that, so claim 2 is going to be that phi 1 ZdPQ of omega E is smaller or equal to phi 0 ZdP prime Q of omega E for every P smaller or equal to P prime. And maybe not to make a mistake, I'm going to try to have consistent formulas with, so the P, I'm going to put a P prime here and a P here, like that. This is going to be claim 2. And once we are going to have this, we are going to deduce that, in fact, phi 0 ZdPQ of omega E is equal to phi 1 ZdPQ of omega E for every E for, so maybe just before we prove, conclusion of the proof. If we are at a continuity point P0 of the function P maps to phi 1 ZdPq of omega e, if you are at a continuity point like that, what do you deduce? Then phi 1 P0 of omega e is equal to the limit when p tends to P0 of phi 1 ZD PQ of omega e. But this guy being smaller than the same with 0 for omega PQ, it gives me this inequality. Since the other inequality is even more trivial, if phi 0 ZD P0 Q of omega e is clearly smaller than that, then you have equality, and by claim 1, you get, so you get that the two measures are equal. Since phi 0 ZD P0 Q of omega e is also smaller than phi 1 ZD P0 Q of omega e, we deduce by claim 1 that the two measures are equal. So the last step is we conclude by observing that P gives phi 1 ZdPQ of omega e has countably many discontinuity points. So this is just a conclusion, but of course I still need to prove claim 2. So what I need to prove is that as soon as I take different p's, it's not possible that the big measure, so phi 1, is larger than phi 0. So let A be phi 0 ZD PQ of omega e, and B equal phi 1 ZD P prime Q of omega e, and remember that P prime is smaller than P. So you take big boundary condition for the small measure, for the small P, and zero boundary small boundary condition for the big P. Okay. So second thing is that let's so if P or P prime is not equal to 0 or 1, which are trivial cases, then, or which you can automatically assume are maybe discontinuity point, but it's not important. So we are going to assume that A and B are strictly between 0 and 1, and in fact, pick epsilon such that you even have that. Okay, so we know they are strictly between 0 and 1, or we assume they are strictly between 0 and 1, and we take an epsilon like that. Pick also n, and observe the following. So first thing is that phi lambda n pq of omega, remember that omega is the total number of open edges. It's smaller than a times the number of edges in lambda n. That this thing is smaller than a times the number of edges in lambda n, simply by monotonicity. So this is the sum of the phi lambda n pq of omega e, but phi lambda n is smaller than phi on zd, therefore you get this inequality, and that implies in particular that phi lambda n pq of the event that omega is larger than a minus epsilon e of lambda n, this is larger than epsilon. This is just larger or equal to an epsilon. In order to derive that, it's just observing that omega is smaller than e of lambda n and just use the Markov inequality. In the same spirit, phi lambda n ghost pq, p prime q of omega is larger or equal to b times e of lambda n. This is just using the domination in the other direction. And this implies that phi lambda n ghost p prime q of omega smaller than b minus epsilon e of lambda n is smaller than epsilon, is larger than epsilon. Sorry. Okay? So these are really two trivial inequalities involving the definition of A, B. Now, observe that phi lambda n ghost p prime q of any observable x can be rewritten in terms of the lambda n p q observable by doing the following. So first, I'm going to look at the edges in the box of size n and observe that for every open edge, the parameter is p prime over 1 minus p prime instead of p over 1 minus p. So I need to multiply by p prime over 1 minus p prime, 1 minus p over p, to the number of open edges in omega. So this is number of open edges in E of lambda n. I'm not counting the open edges of the additional edge connected to the ghost. So this is the first thing I need to do. And the second thing I need to do is I need to count the clusters in a different manner. Why? Because in this measure, I'm not counting any clusters. Why in this, I'm not connecting any clusters or counting any merging between clusters in different boxes. Why here, I'm counting. So there is an additional, let's call it capital K of omega, which is something that is counting differently clusters. And here, I can do the same with p prime 1 minus p prime, 1 minus p over p to the omega k of omega. Now, in any way, whatever the k is doing, it cannot be worse than maybe it doesn't merge any clusters together, or at worst, it merges all the clusters that touch the boundary together. So the important thing is that the k of omega is in fact larger or equal to 1 and smaller or equal, smaller or equal to 1 and larger or equal to k, q to the minus the size of the boundary. So this is something you can easily check. So overall, now if I look at all of this together, I end up with the fact that epsilon, let me take that to be certain not to make a mistake, that epsilon, which was smaller or equal to phi lambda n ghost p prime q of omega larger than b minus epsilon e of lambda n. Well, this is smaller or equal here by using the bounds on q and on lambda. It's smaller or equal to q to the size of the boundary times phi. What am I doing? Phi 0 lambda, phi lambda n pq of, let me maybe call this quantity here, let me call it lambda, just to make my life simpler. So lambda to the omega indicator than omega is larger than a minus epsilon e of lambda n. And here I meant smaller, and there was a plus that I forgot. This is where you need an audience. Divided by phi lambda n pq of lambda to the omega. Now lambda is smaller or equal to 1, so I can just forget about this inequality here. And I get smaller or equal to q to the boundary of the box divided by, well, phi lambda n pq. Sorry, I cannot, of course, get rid of this one. That this one that I can get rid of, this is smaller or equal to 1, so I get smaller than this times phi lambda n pq of lambda to the omega indicator than omega is larger than a minus epsilon. Sorry, that was still not the case. Here I'm still with a b plus epsilon, so smaller than b plus epsilon e of lambda n. But here, because I have this inequality, okay, I'm really sorry, but it's difficult for me. So here what I'm going to add is I'm going to add an indicator that omega is larger than a minus epsilon e of lambda n. This is authorized. So if I use now here then omega is smaller than b plus epsilon e of lambda n, I can bound this by lambda to the b plus epsilon lambda n, e of lambda n. And downstairs, using this bound, I can bound by lambda to the a minus epsilon e of lambda n. And both things together give me times epsilon. So here I'm bounding the lambda to the omega by lambda to the a minus epsilon e of lambda n. And maybe I should. And then I only get larger than a minus epsilon e of lambda n. So overall, I get smaller than q to the lambda n, lambda to the b plus 2 epsilon minus a e of lambda n, and I get divided by 1 over epsilon. When I see this quantity, what do I deduce? When n goes to infinity, in order for this to make sense, you need b plus 2 epsilon minus a to be smaller or equal to 0. Otherwise, you have a problem. And that implies that I made a mistake. It's a minus 2 epsilon here. So this implies that b must be smaller than a plus 2 epsilon. And since this is true for every epsilon, that implies that b is smaller or equal to a, which was what we wanted to prove. So you see, it's a little bit tricky bound. So I just realized that it's a catastrophic thing. So everything was wrong everywhere. So this was a plus. This was indeed with a minus. And here it was with a minus. And here with a plus. So, and now we get this thing. Yes. Okay. I surely hope that if there would have been people, they would have noticed that this was weird. But here it is. So this is the proof. So it's really based here, just to conclude, it's based on the observation that if there was a too big intensity, like edge intensity, at a smaller p, then it will kind of give a boost, but the problem, I mean, it will contribute here to something which is exponential in the volume of my box. Why? The fact that you are giving a boost, you are looking at the ghost thing, is giving you indeed a boost of q to the number, to a certain number, but it's exponential in the size of the boundary. So it will never be able to overcome this quantity when n tends to infinity. So that gives me the inequality I wanted. That gives me uniqueness for all but countably many points. And from there, I deduce that the long-range ordering critical parameter must be equal to the long-range ordering, the magnetization, the spontaneous magnetization critical parameter. And that concludes this section. So next week, we will do the equality of the magnetization parameter and the exponential parameter. So at the end, we will have equality of the 3 parameters I introduced 2 weeks ago. Thank you very much for your attention.